Hello everyone, how are you all doing? Sorry for the glitches that we've been having the last few days, but the whole idea is now that we get this sorted now. Can you guys hear me clearly? Hello, the idea is that you use the Q&A section to ask the questions. All right, that's the goal. Yes. There's a session, guys. We're trying this out. That I have some sessions on Zoom and simultaneously broadcasting onto YouTube. If you prefer to have your questions answered, it'd be nicer if you guys are logged into the Zoom link that I've shared. But this is when it's starting right now. I just need one more minute, but I'm thinking you guys can hear me well enough. Hanan, Abdurrahman, can you hear me? Live in class, Dilaver. How are you doing, Dilaver? Yes, this is also live broadcast. Sir, can I flex that I will get to meet you face to face next year? Saad, inshallah, if we both stay healthy and alive, inshallah we will. Yes, I'm flexing that I'll get to see you next year. How about that? How? I think he's thinking of coming to the college. I teach A levels, and that's what he means. Okay, so basically, people in the Noor Academy can join Zoom. It's a free login to join. I have already said that. You can also, I'm also looking at the chat on YouTube just in case, since it's the first time. But the YouTube chat is a 15-second delay. Hence, so people. Okay, so I've piqued your interest, Asad. Thank you very much. The rules still apply for those of you logged on to Zoom with me. The rule is that I need you guys to understand that I need you to use the Q&A to ask questions, all right? And obviously, this will, get better with time, obviously, all right? And I'm going to try to explain to you the next idea that we'll be doing. So you can join, absolutely. You can watch the class on YouTube or Zoom. It's exactly the same class. No, Zoom Academy is not gone. That's the thing. What they have on their platform, I don't have, which is access to ability to do a lot of questions and quizzes and all that stuff. So what we'll do is we'll use both platforms. When I want to teach theory only, I'll try to use, we are working on using this. And I know it's your future at hand, but trust me on this one, I care as much about your future as you guys do. That's why I'm trying to do as much with my time as possible, which is giving you guys more time, combining both Noon Academy's platform and Zoom, because their platform is still being worked on and they're improving it on a weekly basis. So till we get to the place where I can use their teaching canvas, for the teaching canvas bit, I'll use this, but for doing past paper questions and Q&As and MCQs and other quizzes that will happen once to twice a week, we'll be doing on their platform. So I will sort this out, and then I don't want to cancel any more classes, so I'm starting today. But if you could forgive the randomness for another day or two, and then we'll be sorted back into life. But I'm glad I'm back on something that's familiar with me. We will be looking at metallic bonding and structures, and hopefully recap some of the things that are lost. Some of you are interested in the earlier lectures. Once the platform solidifies, I will make all the earlier lectures uploaded on a particular platform, both Noon Academy and YouTube, so all of you can see the earlier chapters. All right, anyways, so are there any particular questions before I begin? Q&A works. I've got my Q&A open. I've got my chat on both places open. I'm trying. Yes, Asiful Islam, this is as live as it can be. It's a 15-second delay, but it is absolutely live. So I'll wait for 10-15 seconds to get your feedback because there's a delay, but then it won't be that. Then we'll continue with live. All right. Sorry, any questions? All right. Where's the Zoom thing? Where the hell is the Zoom thing gone? Oh, it's right there. All right. So will the stream be saved on YouTube? Absolutely, this stream will be saved on YouTube. And the stream's link will be also posted in Noon Academy, so that's easier to find. All right. I can start. Yes, thank you so much. All right. Okay, there is a 15-second delay. All right. That's sorted. That's sorted. What else? Who else? What does POG stand for? I have no idea. Does anybody tell? I didn't understand anything you said about the Noon Academy and Zoom. Hanan, so what we're doing is we're working towards the lectures. Okay, I have no idea what Pogger's champion is. Clearly, I'm becoming old now and inconsequential. Hanan, I was saying is that I said that in Noon Academy's platform, I'll be doing past papers along with Q&A sessions and tutorials. And the lectures will be on Zoom. So we'll use both platforms. And I'm sorry it's that way because what they have, I don't have. What they have is a way of quizzing you guys, testing you guys. And so the practice that we need for past papers, they have a platform that is much more robust than Zoom can ever be. So we use that for that while we are using this. All right. Abul is right here, by the way. He is not speaking, but maybe we can have him log in with his mic also. And Abul, can you speak? Hello. Hi. So we don't have, yes, Asba. Yeah. Okay. Okay. So we have some really, really random ass comments coming in from somewhere. I shouldn't use that word, sorry. I meant random comments. All right. So Abul is typing out because, yeah. Anyways, so he's literally sitting next to me. Or is literally sitting next to me. Yes, I believe he has missed you too. You know. So today's goal was to start and finish metallic bonding and metallic structures. All right. So that's where we begin from. If you don't mind. Okay. So today's last. Yes. Trust me, my classes are generally more efficient than what they have been, but we're getting to that now. So, anyways, Abul is trying to flex his muscles both on YouTube and Zoom. Hi, Abul. He's here, right here with us. Yeah, I know. He's the fun one. I get that. I know. Yeah. All right. So where were we? I was going to go with you guys with. Yes. So now we're going to discuss metallic substances. So now let's look at the screen now. And I get that in front of everybody. Yeah. Okay. Dilavar, you're face forming yourself. I don't understand. All right, so let's talk about what are metallic substances. We know what are metallic substances, also known as metals. Now, the reason why we call something a metal is basically they have certain properties. All right. Now, metals are basically how we divide elements into. So if you remember, one of the earlier classes we had divided elements into metals and non-metals. And what we have discovered is that metals have a certain structure that we call a metallic structure. And non-metals tend to either have giant molecular structures, which is only a few giant molecular structures. Some of them have that. And many have simple molecular structures. These are just elements, okay? Not molecules, not compounds, just elements. Metallic structures could be things like iron, could be sodium, could be magnesium, calcium, that stuff. Non-metals, which are giant structures, contain things like diamond, things like silicon, simple molecular, there are only a few. And simple molecular substances are things like elements, like noble gases are just going to be monoatomic, like helium, argon, neon, and then you have oxygen, nitrogen, chlorine, fluorine, bromine, iodine, many, sulfur, many. And these are all so when you have elements, I'm not talking about compounds right now, I'm only talking about elements. And when I'm talking about elements, then the only elements are very easily divided into metals and non-metals. In fact, if you look at the periodic table, which I'm just making a very rough sketch here, if you're familiar with the transition elements too, then what you realize is that most of the elements are metals, and there's a staircase of sorts, and what the idea is that all of these groups 1, group 2 transition elements, some group 3 and so on, are metals, and only very few are non-metals. And I will include graphite. I did not mention graphite yet because we will talk about them later, but yes, we can. And anybody who's in the Zoom chat, please, I will recommend you please use the Q&A section to ask the questions, because I can't look at 5 different pages to ask questions, please. So again, those who have joined me on Zoom, please use the Q&A button to ask questions. And for those of you who are on YouTube, you can use the YouTube chat to ask questions, but I will be 15 seconds behind for those answering questions in YouTube. If anybody's here talking about AS level, please, this is an O level class. All right. So continuing with this, also, I'll shamelessly say this in class recorded. Please subscribe to my YouTube channel. I've never said that before, and now that I've hit 10K subscribers, I think I can say that to some of you, that please pass the word around. I get no money from YouTube. I just get a sense of accomplishment from that number. All right. Anyways, there's a bell icon as well. Okay. That bell icon. So thank you. All right. So I was just saying, so all of your elements can either be metals or non-metals. Metals have a metallic structure. Non-metals are either simple molecular structures or giant molecular structures. If my writing is horrendous, even I couldn't recognize this. So I meant simple molecular structures, like, and they have low melting and boiling point, and you have giant molecular structures. Now, you will not find ionic bonding in this at all, because ionic bonding is for compounds. This is for elements. Okay. Anyway, so yeah, but there's no ionic bonding here. This is only for elements, and metals have a certain properties. So when we say what are metallic substances, we really mean that their elements have certain properties. What are the properties of the elements? Okay, let me just sort that out here. Just 1 second. Giving that up. Just 1 second. All right. 1 second. Sorry, just 1 second. What happened? What happened?
Your video isn't showing. This is your profile, no?
Yeah, I've stopped the video. There you go. I just want to screen. I just want the screen. Yeah,
but your face isn't showing.
I don't want it to show. Okay. Fuck it. अभी बाद में करेंगे. What's written next to iodine? Okay. Actually, iodine was here. I2 is S8. Sulfur is found as S8. Okay. And here I had written iron, sodium, calcium, magnesium, other metals. All right. Okay. Okay. And this is supposed to be graphite. Thank you. Diamond, silicon, graphite. Again. All right. I've answered that bit. Okay. All right. All right. Anyway, so this is what we have. So let's talk about some of the properties of metals, and then we talk about why they exist. So because it's easier to remember, because this is one of the few things in chemistry that you know from real life examples, you know what metals are. Now, we'll talk about the structures later, but first let's talk about some of the properties we know, because the properties help us remember their structures. Now, what are some of the properties of metallic structures? We know that metals will conduct electricity in the solid state. They are the only things that conduct electricity in the solid state, except for one exception, but now there are a few, but generally, traditionally speaking, any metal will always conduct electricity in the solid state, while generally non-metals or macromolecules or simple molecules or ionic compounds do not conduct current in the solid state. They do it in other states, but not solid. Yes, there are a couple of exceptions, and we'll get to them later. Right now, I'm just saying they don't. All right, for most of us. Anyways, so moving along, what we have? Yes, so first thing is that they conduct electricity in the solid state. Secondly, most have high melting and boiling points. Most, except for group 1, most have high melting points and boiling points, and except for group 1. And we'll talk about why. The structure will help us understand why they have a high melting and boiling point. All right. And then what else? So this is the two things. One more thing is that actually two more things. They're generally also good conductors of heat. So they're good conductors of electricity and good conductors of heat. That's why most of your pans, cooking pots are made of metals, because they both have high melting points, but they also conduct heat. Like other substances exist that have a high melting point, but they're not good conductors of heat, like the bricks that you use for houses. So when you don't want heat to transfer, we use ionic compounds like bricks. So the bricks that you use for houses are ionic compounds, but the pans you use for cooking or the lining of your the kettle pots are all metals, because metals are good conductors of heat, but they also have a high melting point. Also, they are what we call, metals have a very unique property that only is unique to them and nothing else. They are what we call malleable and ductile. Now, in very simple terms, what does this term mean? Malleable and ductile. Now, malleability and ductility. Now, this is for those of you in Pakistan where it's very difficult for us to understand English, and then they throw this words like malleable and ductility. And the word malleable simply means this, and ductile in English is like, if you ever, like a good example to think about, the difference between metallic structures, ionic structures, and simple covalent structures, is that metallic structures are like your spoons and knives at home. Ionic structures are the cements and the bricks that you use to build a house. And simple molecular structures are the gases you breathe in and you breathe out, and the liquid you drink, right? Generally speaking. Now, between that, so for example, if you take a hammer on an ice, let's say an ice is also a simple molecular structure. If I take a hammer and hit ice with it, what will happen to the ice? It'll chip, it'll break, tuck, tuck, things will happen. Do you agree? Yeah. Then the second thing is, if you take a hammer to a brick, like a big hammer to a brick, now you hit that brick with a hammer, it'll also chip and break. But if you take a hammer to a metal, it'll never chip. It'll just flatten out or it'll bend. So when metals flatten out, bend, that's because we call them malleable and ductile. All right. On the other hand, everything else is what we call brittle. So the opposite of malleability and ductility is brittleness, or being brittle. Brittle just means, it doesn't mean strong or weak. None of these mean strong or weak. They're both properties. Meaning that if you hit something and you break it, chip it, it's brittle. If you hit something and it bends and it turns, flattens, it's malleable. They're literally opposites to each other. So that's how you can remember. Okay. Anyways, so yeah. So we got malleable, ductile, and brittleness. All right. Okay. Yeah, just 1 second. Okay. Anyways, moving on. So that's some of the properties. So 3 properties that I want to discuss with you today are what's common to the structure of metals. And it seems very easy because if you learn this, and most of you have already done this because if you're in 11th grade and last year of O-level chemistry or IGCSE chemistry, you've done bonding way long ago. Okay. Now, you might know the structure of metallic structures. So I want to make sure that I talk about things that you might not know of, that you still have to be aware of. All right. Now, what do we have going for us right now? What we have is understanding that metals have certain properties. They conduct electricity in the solid state. They have high melting and boiling points, except for group 1. Group 1 is actually soft and low melting points. But that's because of the kind of structure they have. And they're all malleable and ductile. So conducting electricity, high melting and boiling points, and malleability can all be explained by the structure of metals. So what is this structure of metals? Now, metals are solids, and what we know about solids is that solids are a lattice. Every solid is a lattice. So metals are solids at RTP, obviously, except for one really interesting fellow called mercury. Mercury. It's a liquid, but most all are metals. All right. Can you hear me? Sorry about the shuffling. Now, before I discuss the structure, okay, are there any questions you want to ask? All right. Anybody? Any questions you might have? You want to ask? Not so far? All right. Okay. So, and what do you know about? So there are solids. What's a solid? Solid has a lattice. What is a lattice? A regular arrangement of particles. The particles could be atoms, ions, molecules. That's what a lattice is. A lattice is a name given to anything that has a regular arrangement. We saw a lattice in, let's say, ice. Ice, if you remember, is a lattice of molecules of water. So each of these circles in ice that vibrate about a fixed point are water molecules. If we have iodine solid, which was where each circle is I2, which is I bonded to I. Then this was non-metals. Then we saw lattices in ionic compounds, which are simply just a lattice of cations and anions. And again, every solid can be considered a lattice because every solid has a regular arrangement of particles. That's what we know. So here I'm repeating the same diagram for the umpteenth time, but I think after today I will never have to draw this again. But this is the ionic lattice. Lattice is just a regular arrangement. The guys on top are called molecular lattice. Lattice in English just means a regular arrangement. And because metals are solids, they must also have a lattice of something. So I'm going to show that to you now. All right. Coming up. All right. So that was done. Is Hess law related to lattice enthalpy? Rahul, that question that you asked me would make more sense in A-level second year. So we don't speak of such things as double sets in Yes, he's absolutely right. That's an AS level, A2 level question, second year A levels. Okay, so now I have this. Now here I'm showing you a nice little diagram of a lattice, because if you notice these purple outlines, those are the atom. You see that? Atom. So this is a lattice of atoms. So you can think of metals as a lattice of atoms. It really isn't a lattice of atoms, but let's call it that for now. Now, so basically, if I'm talking about, let's say, sodium, which is Na, sodium has 11 protons and it has 281 configuration in 11 electrons. So these would be, each of these would be a sodium atom. So this highlighted circle is just that. It is one sodium atom. But something happens to metals. All right. Okay. Now, what is something that happens to atoms? Well, when they become a metallic structure, a very unique, and don't ask me why, because I can't explain the why to you in the knowledge that we study in O levels, neither in A levels. But when we take enough metals together, you see the problem with non-metals is that they can share electrons to become an octet. The metals, like sodium, have to lose electrons to become octets. And if I have so many sodium atoms, they cannot lose electrons to each other because they just can't. They have to either lose it to somebody else who wants to gain it, and even if they were to share one electron each, they will still not become an octet. So how do I make something an octet? Very simple. It doesn't happen here. So what they do is they kind of lose their outermost electron because they have to lose it, remember. So when metals, the only way for metals to become an octet is by losing the outermost electron. But if I had chlorine atom alongside it, which is how we made ionic compounds, the chlorine atom would take away the electron of sodium, and that would have made an ionic compound. The problem is we don't have chlorine atoms if I only have sodium. We have only sodium atoms around it. So for the lack of chlorine atom, who does sodium atom lose the electron to? They lose it to, you can call it a common bank. They put all of the outermost electrons into a common bank because they want to lose it, they want to get rid of it, but they can't. So they all collect it. And what happens is that every single atom puts into the bank its outermost electron. And what happens is those outermost electrons get shared amongst everybody. And we use the term like delocalized. What happens for metals, and this is, if you've never heard this idea before, I know this is unique and it'll knock your socks off, but this is what happens with metals. What happens with metals is that they lose the outermost electron, and every single atom in the layout, kind of like, think of it like a pool. They put it if you've ever played a game of cards, you put something in the bank or the central place that you want to store it. So elements do that. Atoms of the element will do that. They'll put all the electrons in a common bank, and then they are shareable to everybody. That's the idea. And because these electrons are easy to move, and you know how we know that? Because that's the only way current would be conducted. Because what is conduction of current? Conduction of current is simply movement of electrons, because that's what a current is. Current is movement of charge, and that's what these guys do. So let me go through this in a little more detail, but I'm going to talk about the fact that if you have any questions about just the fact that right now I've made a lattice of atoms, and then I've said since sodium has, let's say, 281, the outermost one has to go somewhere to be stable. It goes into a common bank and it gets delocalized. Where's the delocalized? You see the purple dark circle? That's your delocalized space. And if you can look at this, there are 12 atoms here. So the 12 atoms shown here, their outermost electrons will be 1 each. That makes it 12 electrons. So all these 12 electrons are moving around here. Like you could have them all in this space right now on the left. In the next moment, they can all have moved there, depending on how you move electrons. And if you take physics, you know that you can have electrons move from one area to the next if there's a shortage of charge or electron. Like for example, if in chemistry you know that negative attracts positive. So if you put a positive electrode on this side, all the electrons will move to that side. And that's how we conduct current. So the outermost electrons are not really, you could say they're shared equally. So this is the metal's version of sharing electrons, because they cannot just share two of them, because two of them will not make an octet. Just like if you noticed when I was doing this with you guys for a second here, let me go back. And when non-metals had to make an octet, they had to share electrons, and they became diatomic molecules like O2, N2, Cl2, F2, Y2. You can't have that with metals. Metals won't do that. And because even if two were to combine, they would still have not achieved the octet. So that's the biggest problem they have, not being able to achieve the octet. So what they do is all of them combine in the delocalization. All right. And when they all put these electrons and they're shared equally, that shared space is called the delocalized space. So I'm going to pause here for a second and wait for some questions before I continue. And I'll repeat some of the stuff again, but I want to make sure that there's something that you have, nobody's really confused about something major right now. Saad, I believe I answered your question. Yeah. Guys, for those of you who are involved in YouTube, I realized that maybe I have to, figure out a way that blocks the whatever. There's always somebody else who thinks they're smart enough to log in and just whatever, Now, this delocalized space, for somebody who's mentioned something, and no questions, huh? Okay, so basically this is referred to many books by a sea of electrons. So let me see if I can highlight that region again. You see all that purple region that you can see a color shading come, maybe you see it. That's basically, you can think of it like a common area where all the outermost electrons are moving about. So the 12 electrons are moving about here randomly. They can be like la 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 la, moving around, moving anywhere. So because what you have is 12 atoms here, they have 11 electrons each, but it's only the outermost that gets to move around here. You see, and you might wonder, well, that's one electron. Well, if this was not sodium but magnesium, if it was magnesium has 12 protons, but its electrons are 282. So for the same thing for magnesium, it would be that the outermost 2 electrons are shared right here, shared all across. So for example, in the same delocalized region, if for 12 atoms you have 12 electrons for sodium, for magnesium there will be 24 electrons in this region. For aluminum, there would be, because aluminum has 3 electrons in the outermost shell, for 12 atoms, there will be 36 electrons that are moving from anywhere from this corner to that corner. The beauty is that when we say delocalized, what we mean to say is that they no longer are localized to one area. Localized means being in one area. The inner shell, for example, if this was sodium, if this circle is sodium that I'm pointing to, it has 11 electrons. 10 of the inner shells remain in this space. The 11th one is free to move anywhere. It can go anywhere it wants. And the same applies to every single atom here. So every single atom here, if it was sodium, has 10 electrons in the inner shells not moving anywhere, but the 11th one is free to move anywhere it wants to. Right there. Now, if it was magnesium, and if all these were magnesium, then the center will be the nucleus, and 2 and 8, which is the inner shell electrons, are moving around in, and 10 in the same space. But 2 of their outer electrons can move anywhere here, anywhere there. So for magnesium, you've got, for 12 atoms, you'll have 24 what we call delocalized electrons. For aluminum's 12 atoms, we'll have 36 delocalized electrons, because it's all the outermost electrons being shared. Noman, does it make sense to you now? Muhammad Ali, is something similar happens. This is exactly what happens even in there are many. Yes, basically all the outermost electrons are free to move around, hence the term delocalized. So the outermost electrons from the outermost shell, they become delocalized and they are free to move anywhere. And because these electrons are free to move anywhere, that's why they can conduct current, basically. All right? That's literally why they can conduct current. Does that answer your questions so far? Noman, does it answer your question? All right. Anybody else who has a question about this? I mean, I can put in more diagrams, and I would like to. And I'll talk about bonding. So this is what happens. Let me show this to you. I got a beautiful, beautiful diagram right here. I'm a diagram hog. I love diagrams. I keep telling a bull, let's find more and more diagrams, more and more, as many as we can find. So here is that. For example, let's talk about aluminum. Let's actually say magnesium. So let's say this is a magnesium, Mg. Now Mg has 12 protons. What happens is that the outermost are shared. If the outermost are shared, those are the pink ones. So these ones are these pink ones, And if you notice, there are arrows drawn here because that means they can move anywhere. They're moving freely. And what's left is this blue guy is now just simply magnesium with only 10 electrons. So when it's magnesium with only 10 electrons, you'll realize that this fellow has 12 protons but 10 electrons. It's lost the outermost electrons, so it's become a cation. It literally has become a cation of sorts. It becomes Mg2+. So basically these guys are Mg2+. All of these. So instead of being a lattice of atoms, it becomes a lattice of cations without the outermost electrons, and all the outermost electrons are in this shared space that you can probably see, this highlighted light brown color, whatever, and they can move around in this space freely. And all of these pinks can mate to go left or mate to go right. And the positives basically are being attracted by these negatives. Think about, so what I want you to imagine is the delocalized area that I'm highlighted here, and maybe I can do a better job of highlighting it with the yellow. Maybe. I don't know if this works for you guys. I don't want to lift my pen right now. But you see the yellow region that I'm highlighting here right now, right? Now, think of it like glue, because it's literally glue to the metal. Why is it like glue? Because this is the space where electrons are in. So if I were to ask you what charge would this space have, this yellow highlighted space would be negative space. It would have a negative charge, right? Okay, I run out of space here. It'll have a negative charge. All right? Yeah. Anyways, yeah. Anyways, moving along. All right. Okay. So where were we? Yeah. So basically, this yellow region can be thought of as a negative charge, and the positive space, so basically, yeah, the negative region is this yellow area is the negative region, and all these circles are cations, positive. So yes, the cations might have been repelling each other because they're both positive, but because they have this negative glue or goo or liquid between them, you can think of it like that, then they stick in place because they are being attracted. Okay, so the lattice of cations is this blue space. So the blue are your lattice of cations. Okay. While the yellow is that negative glue that keeps all of these particles together. And because this negative glue is attracting so many positive particles, that's the electrostatic attraction. So metallic bonding really is, there is force of attraction. So there is electrostatic attraction, just like all bonding has to have. The word bonding means attraction. So it's electrostatic attraction between cations and the delocalized electrons. Delocalized electrons. And that electrostatic attraction is so strong, that's why, yes, Areeb, this is part of all chemistry. IGCSE, O levels, grade 9, A levels. You can't get out of A levels without studying this stuff. All right? So what was I saying? I forgot something I was saying. I don't remember. What was I saying? Yes, I was saying that there is an attraction between the yellow area, which is negative, and all the positive blues. And that is electrostatic attraction that gives the rise to the name metallic bonding. This attraction is what is metallic bonding. And the greater the attraction, the stronger the bonding. All right. So first of all, this attraction is already very strong, which means that they have a high melting point. Second, these electrons are free to move left or right, which is why they can conduct current. Hence, two of the three properties we've got. One is they have high melting points because this electrostatic attraction is very strong. And you have to separate, even though you might think, well, why aren't the cations repelling each other? Because in the space between them, the glue holding them together is the electrons that are delocalized. And that makes the melting point high. Then what is current? Current means pushing electrons from one side and going them to the other side. And when we pass current through a metal, like if you were to put, like how does a light bulb work? Literally, the electric power supply company puts electricity on one side and electrons from that go through the whole metal to the other side. That's what it means to conduct electricity. And that's that. Then, so therefore they conduct electricity and they have high melting point. I'll talk about the third thing in a minute, malleability and ductility. Why are these malleable and ductile? But before I do that, I want to talk about how can I increase this attraction, obviously, right? Because if the cations and the electrons are attracting each other, how can I increase this attraction? You know, and that has to do with the electrons, and the shared electrons. If you guys just give me 1 second. Yeah. Yeah, just 1 second. Putting up a nice little diagram, okay? Patience, everybody. Patience. So, here is one. Okay, so one diagram a little here. So, obviously these electrons are moving. Now, I want to compare this to, let's say, a very good conductive metal. You got a heard of copper, ain't you? Okay, now in copper, and I'm taking these from random places, so they might not be the exact same book, but you get the idea. Now here you can imagine that I have got sodium on the left hand side and copper on the right hand side. Now copper, or for the sake of, let's not use copper, let's change this, okay? I tell you that ignore that because I don't want to talk about transition elements right now. I'll say assume this is magnesium. Now sodium is 281. So each of these is a sodium cation and there's only one electron in the delocalized part. This class there is ending in 10 minutes, all right, till 6 o'clock. All right. Magnets, I'll get to there later, Muhammad Ali. Now, on the other hand, in this particular, on the diagram on the right, I have magnesium. Magnesium has, each cation is 2+, first of all. and it has twice as many electrons in the space. So the space that we were talking earlier, this empty space that I'm highlighting with my yellow, this delocalized space in magnesium has twice as many electrons as the one on the left. The one on the left has, if whatever it has, the guy on the right will have twice as many electrons, which means two things. Is that first of all, the electron cloud has twice the negative charge. And the cation has 2+. What that means is the electrostatic attraction here on the one on the left, on the right. Attraction, my writing has to get better. Electrostatic attraction is greater in magnesium, which is why magnesium will have a higher melting point than sodium, because greater attraction here. All right. So magnesium is definitely going to, so basically why am I explaining this? So the attraction is greater, therefore the melting point of magnesium is much greater than the melting point of sodium, because magnesium's metallic lattice is stronger than sodium's. Why? Okay, so I'm not telling you there's a net charge, Saad. Obviously the charges balance out, but the force of attraction in anything, remember, the force of attraction depends on the magnitude of the charges attracting each other. The same reason why in NaCl's melting point was lower than MgO's, if you remember, in ionic lattices. MgO is twice as much attraction than NaCl because of the charges. Here also Mg's cations will attract the electron cloud twice as much as the sodium metals. Alrighty? Does it make sense? Again, they want this part, this little part, they might not test you on, but you should be aware that the strength of metallic lattices is because of the size of the charge on the cations and the delocalized electrons. That's the key. That is the key. So aluminum will have a higher melting point because aluminum has 3+. All right? Okay? So have I answered most of the questions? Because I'm going to talk about the last bit now, the malleability and the brittleness. All right? How are the questions asked? What do you mean, how are the questions asked? You just type them out like you just did? Muhammad Ali? I don't know what you mean by. Oh, you mean how the questions asked in the past papers? Oh, we'll figure that out in the next class and we solve the questions for this in the next class. Not right now. Asbah, absolutely. Higher the number of delocalized electrons, which means the cation's charge is also greater. Therefore, stronger melting point, higher melting point, stronger attraction, more delocalized electrons and higher cation charge, strong metallic bonding, higher melting point. Absolutely. All right. Then anyways, moving along. This is done? Yeah. Okay. Uske baad, so last thing left now. All right. Anyway. Okay. So, moving along. Okay. Anyways, this is O-level chem. Somebody asking me, but I don't know what they're asking me. Okay, anyways. So, now the next thing is, so when I was saying earlier, if you hit something that's brick, when you hit something, why are metals so malleable? Why when I hit them, they move? And why? Versus, like if you ever take a chisel and a hammer to a brick, when you hit it, it chips off so cleanly. Have you, like if you take, so bricks for that matter, I'm sure when you're growing up, you played a lot of things. I mean, like with stones in the ground and all that stuff. And stones and bricks, when you break them or chip them, they cut off very cleanly. They chip off very like sharp. Same with ice sometimes, right? So now, why does that happen? What happens is that when you're ionic lattice, first I want to talk about ionic lattices, then I'll talk about this. Again, this part, what I'm just going to explain to you is not needed for the exam. This part is just to explain to you why they're malleable. And I just want to spend 5 minutes explaining that because it's a good thing to have. Now, one second. So when you basically hit an ionic lattice, so imagine this is your brick and you've hit one corner of it with a hammer. When you hit them, the ions move around. They get moved, they get hit, and the way they move is that suddenly, instead of attracting the guy in front of you, they're aligned with the same charges. So the moment they align the same charges, suddenly, instead of a force of attraction between the opposite charged ions, they are suddenly going to repel each other. What I'm saying is that these highlighted ions get pushed down, and when they get pushed down, they end up facing each other, which ends up creating repulsion, which is why these guys are brittle. So ionic compounds are brittle. This is an ionic lattice. An ionic lattice is brittle. All right. On the other hand, metals don't do that, because even if you hit them, they are not going to repel each other because of the glue. Remember, the delocalized electrons are glue. They are literally glue. So yeah. So when I'm show you diagram, what really just happens is they move. Nothing else happens. They do not repel each other because they have a glue in between. I'm trying to copy the diagram. It ain't happening. Come on. 1 second. There you go. Wait a minute. So first what's happening, then why it happens for metals. So this is what happens in a metal. You have a metallic lattice. You hit one side. All they do is they shift, but they don't repel each other because there's a glue holding them together, and that glue is your delocalized electrons. That's what's happening. And I had a very beautiful diagram Abul gave me, and I can't find it. I need to find it. It's here somewhere. Oh, come on. Oh, come on. Okay. Wait. I know I have it somewhere. Yes, there it is. So because of the delocalized space between the cations, what really happens is the cations just slide over each other without repelling. So when you hit, for example, when you hit from one side like a hammer, they do shift, but they still don't repel because earlier they had this glue. Remember, the delocalized electrons is the glue that holds everything together. If they didn't have this glue with delocalized electrons, this shit wouldn't happen. They have this glue that holds it together, and this glue is still there. You see, it's still there. It's still holding the particle, even though they've shifted, because between the repulsion of cations, there is this glue of negative charges which are attracting the cations. So the glue always remains there, which is why they never break off. This is why metals are malleable and ductile, meaning they can be hammered into shape or drawn in thin wires. Yeah. Thank you, Raghav. I think what you said does make sense. Yeah. Yes, you don't break their bonding. You shift the cations, but the bonding is the attraction with the negative cloud that I've colored yellow here. On the other hand, ionic lattices there is a breaking of the attraction, because suddenly when you shift them, the opposite charges attract each other. So there is a repulsion in this case of opposite charges attracting each other here, but now like charges are repelling each other here. So they repel. So ionic lattices are brittle, while metallic lattices are malleable. And if you didn't get this, it's all right. All you have to know for the exams are they have a high melting point. You got to be able to define their metallic bonding. So what has metallic bonding? It's a lattice. So let me write it down for the exams. So lattice of cations and delocalized electrons. Which ones? Outer shell. And there is electrostatic attraction between them, between the cation and delocalized electrons, between them. And yes, they have high melting points and boiling points. They have high electrical and thermal conductivity. Okay, and they are malleable and ductile. Malleable and ductile. All right. So these are the properties of metals. You're going to be asked to draw this and explain this. Sir Abul is the diagram expert, the organization expert, everything. So what if they, so before they do that, Muhammad Ali, they have to come across even the slightest step. You see, when you're asking the question, Muhammad Ali, before they go in front of another like opposite charge particle, they have to first come across a positive particle. What Muhammad Ali is asking, I'll explain this. He's saying, what if this negative, when I hit this guy comes in front of this fellow? Well, it could have, but before that, it would have to pass this fellow, right? And the moment it passes it, it gets repelled out of the system. Hence, it is brittle. All right? Anyways, thank you for the class. I'm going to wrap up. I hope that you guys had a good class. All right? Need feedback? All right? And I don't know how this went for you guys. It was pretty awesome for me. And I'm planning to continue. All right? The Zoom link will be made available on the Noon Academy's website. Please check it out there. And we'll figure out other ways. Recordings are always available on YouTube and earlier lessons also. We'll be moving along. If anybody needs to know what's happening, check out the Noon Academy's My Class section. I post up comments there. But we'll be back on Saturday. Yeah? All right. Anyways. Way better about the... Yeah, I am also am. Yes, Muhammad Ali, absolutely I am. All right. I'm continuing both with Noon Academy and my platform together simultaneously. Whatever it takes to get you guys the best teaching experience, that's what we're working towards. All right? All right? I'm going to head out now and see you guys whenever. All right? Goodbye. You too. Hopefully we're back with an action, kicking and doing it fast now. All right. Bye-bye. Khuda Hafiz.